All right, let's just jump right in. Look, if you've written any modern software, you know the deal. You've fought the battle of concurrency. I mean, how do you download a huge file, hit a database, and keep your UI from freezing up all at the same time? It's like the fundamental challenge, right? And the tools we've traditionally used to handle it, well, they can be a total nightmare.
You know what? Let's just say what we're all thinking. The developer, Mark Murphy, put it perfectly. Threading sucks. And he's right. Why? Because with threads, you're not really in control. The operating system can just interrupt them whenever it feels like it, and that throws you headfirst into this messy world of locks, mutexes, and the dreaded race conditions. Sure, it's powerful stuff, but man, it is so easy to mess up. So, if threads are a pain, what's the alternative? Well, a lot of the time it's callbacks. You know the drill. You kick off a task and just tell it, hey, call this other function when you're done. Sounds simple enough, right? But then you need to do something after that's done, and then something after that. And before you know it, you're staring at this pyramid of doom. This deeply nested, completely unreadable mess is what we all lovingly call callback hell.
What if we could have the best of both worlds? What if we could write code that handles complex asynchronous stuff, but looks and reads like simple, straightforward sequential code? What if we could just escape that awful choice between complicated threads and ugly callbacks? Well, that's exactly the promise of coroutines.
So, what in the world is a coroutine? The absolute simplest way to think about it is this. It's a function that you can pause. Let's really dig into what that means. So, let's be clear. A coroutine is not a thread. Think of it more like a regular function, a subroutine, but with a superpower. And that superpower is the ability to suspend its own execution and then be resumed later on. This whole suspend and resume thing? That's the secret sauce we're going to explore.
So let's trace its life, okay? A coroutine kicks off, running just like any old function. But then, bam, it hits a suspend point. Maybe it's waiting for a network call to finish. And it just pauses. Now here's the really important part. It does not block the thread. That thread is now totally free to go do other useful work, which is a huge win for efficiency. Then, once that network call is done, the coroutine just wakes up and resumes exactly where it was paused.
And this is where the real magic happens. A normal function, you call it, it runs, it's done. Next time you call it, it starts from scratch. A coroutine, it remembers everything. All its local variables, which line of code it was on, that entire state just hangs around while it's paused. It literally just picks up right where it left off.
Now, to really get why coroutines are such a big deal, it really helps to compare them to the things we're already used to. So let's put them head to head and see how they stack up. We've kind of touched on this already, but it's the absolute core difference. A normal function has one way in and one way out. It runs until it's finished, period. A coroutine, though, can have a bunch of entry and exit points every time it suspends and resumes. It's like it's having an ongoing conversation with whatever called it.
Okay, this one is huge. Threads are preemptive. The operating system is the boss, and it can yank control away from a thread whenever it wants. Coroutines are cooperative. They are in charge of their own destiny. They explicitly say, okay, I'm in a good spot, I'm going to yield control now. This means you, the programmer, are back in the driver's seat, and that often means you can say goodbye to all those complicated locks.
So this all sounds amazing, right? But it also kind of feels like black magic. How does a function just stop in the middle and then come back to life later? Let's pop the hood and take a look at the machinery that makes it all possible.
I mean, really think about it. That's the key question, isn't it? A regular function call gets pushed onto the call stack, and when it's done, it's popped off. There's no pause button. So, what kind of illusion is being created here?
The answer isn't in your computer's hardware. It's actually a super clever trick that the compiler plays. Behind the scenes, the compiler takes your nice suspending function and completely rewrites it into something totally different. The technique is called continuation passing style, and it's the secret sauce that makes the whole thing work.
So here's the secret. The compiler takes your beautiful, easy-to-read code and it turns it into a state machine behind your back. When your code hits a suspend point, all it's really doing is bundling up its current state, all the local variables, which line of code it's on, into a little package. Then it just hands control back. Later on, when it's time to wake up, it just unpacks that state and picks up exactly where it left off, as if nothing ever happened. It's an incredibly clever trick.
Okay, so having these super powerful pausable functions is fantastic, but it could also lead to total chaos, right? What if you launch a coroutine and then just forget about it? That's where modern coroutines introduce a truly brilliant idea: structured concurrency.
I absolutely love this analogy from Rashanjot Singh. Think about building a house. You've got plumbing, electrical, roofing, all happening at the same time. The build a house project isn't finished until all those smaller jobs are finished. And hey, if John runs out of money and has to cancel the project, all the work stops. That is the perfect way to think about this.
These are the rules of the road that bring sanity back to concurrency. Every coroutine lives inside a parent-child structure. And this structure guarantees you can't leak work. If you kick off a bunch of tasks inside some scope, you have a guarantee that when that scope finishes, all those tasks are either done or they're canceled. If one of them fails, the whole related operation gets canceled. It makes your code safe by default.
So after all that, what's the big takeaway here? We've gone from the pain of threads and callbacks to this really elegant model of functions you can pause, all governed by these simple, safe rules. So why is this such a game changer for building modern apps?
Because coroutines let us separate the problem of concurrency, which is hard, from the code we write to solve it. We finally get to write asynchronous logic that's actually easy to read, easy to understand, and way less likely to have bugs. And since they're so incredibly lightweight compared to threads, we can run tens of thousands of them without our system even breaking a sweat. It's a tool that admits the problem is hard, but insists our solution doesn't have to be. So the real question is, what are you going to build with it?